Hello, everyone, and welcome to this BNG webinar. I'm just going to give a few minutes for a few more people to join, and then we will get started in just a few minutes. Awesome. I see we've got a few more people coming in, so we'll just keep giving it a few more minutes. Hello, and welcome to this webinar. My name is Lauren Weller. I'm a senior ecologist and compliance lead here at AI Dash. So imagine being able to monitor an entire ecosystem in real time from space. That's the potential, and in many ways, the practice of remote sensing in ecology today. So what is remote sensing? It is a scientific method for gathering information about Earth from a distance using satellites, high-altitude aircraft, and specialized sensors. Remote sensing captures environmental information using sensors that detect light across different wavelengths, including the familiar RGB, red, green, blue imagery, like a camera you would have at home, as well as more advanced technologies like infrared and ultraviolet. Different sensors are used for different applications, and many focus on different areas of the spectrum. Multispectral, for instance, can be described like a camera with a few specific color filters, and it captures data in about 3 to 10 distinct wavelength bands. Whereas hyperspectral imaging is a bit like a super detailed version of a microscope, and it captures hundreds of very narrowest continuous wavelength in bands. It's almost like capturing a cube of data. And by analyzing how different materials reflect and absorb these electromagnetic radiation, and we can detect how specific unique light signatures. And these light signatures can tell us a little bit about what we are looking at. And so you can see whether you're looking at vegetation, rocks, water, or man-made structures. In ecological research, these technologies support critical environmental monitoring by tracking habitat changes, assessing biodiversity, and measuring forest cover. Understanding how landscape transformations happen across vast and often inaccessible regions can be made possible using remote sensing technology. So when we think about remote sensing, we often think about Google Earth, but there is a lot more to remote sensing than Google Earth. So while Google Earth offers a convenient, accessible imagery, it has significant limitations for ecological research. Its algorithms often distort and manipulate images to improve the visual continuity and resolution, which can compromise the accuracy needed for precise ecological observations and area measurements. Fortunately, researchers now have access to a growing range of specialized satellite and fixed-wing imagery providers, and these advanced platforms offer high and medium resolution, positionally accurate and dated imagery specifically designed for scientific and ecological assessment. This provides a far more reliable dataset than many consumer-level mapping services. And so here's an example of some of the things that we might want to do with some of these imagery-based data sets. This is from a paper where they were looking at some of the applications for remote sensing. So you can see here they were looking at things like marmoset burrows from space. They were also trying to look at, for instance, the size of a penguin colony by looking at the size of its guano on the ice. And so there's many things we can use imagery for. They were also looking at things like, deforestation. You can see a lack of forest cover from imagery. And it's just to say that there are a lot of different applications where we are using very high resolution imagery for today. But remote sensing is also not new. And so remote sensing in ecology has a rich history rooted in technological advancements from wartime reconnaissance. In the 1960s, which coincided with the space race, this marked a pivotal moment in the environmental observation. The first images of Earth from space revealed our planet as a fragile blue orb, profoundly influencing the early environmental and conservation movements. In fact, the term remote sensing emerged during this era, with the Landsat satellite program playing a crucial role in developing the technology. Landsat's early sensors included an RGB sensor, which unfortunately failed after just 1,600 images, and a multispectral sensor that captured an impressive 300,000 images over its lifetime. This breakthrough led to the development of the Normalized Difference Vegetation Index, also known as the NDVI, which is now a standard measure of global planet greenness. And an interesting footnote in history is that in 1976, the Landsat 1 actually discovered a previously unknown uninhabited island just 20 kilometers off Canada's eastern coast. It was subsequently named Landsat Island in honor of the satellite that found it. But the evolution of remote sensing has accelerated rapidly in recent years. In the 2010s, we saw a rise of drone-based technologies, dramatically expanding our ability to capture high-resolution environmental data. And by the 2020s, we had satellite constellations and advanced artificial intelligence, which have transformed our remote sensing capabilities and enabled near real-time monitoring of complex ecological systems. These technological leaps have created an unprecedented opportunity for understanding and tracking environmental changes with remarkable precision and speed. But they've also created unprecedented amounts of data. And so we will need AI in order to help analyze this data. Addressing the biodiversity crisis demands sophisticated data management strategies that can handle massive volumes of information. Automated approaches, particularly those that are leveraging artificial intelligence, have become crucial in processing and interpreting complex environmental data sets. Remote sensing generates an enormous amount of data that would be challenging to analyze manually, and this is where the AI technologies shine. Machine learning and pattern recognition, as well as data science techniques, enable researchers to efficiently classify habitats, identify ecological changes, and extract meaningful insights from these extensive data sets. By using AI-powered tools, scientists can now process and interpret vast amounts of remote sensing information, transforming the raw data into actionable knowledge that supports conservation efforts and helps us to understand the intricate dynamics of global biodiversity. So what can we do currently using satellites, remote sensing, and AI? Well, we can use high-resolution satellite imagery for detailed vegetation mapping. That's one of the things we do here at AI Dash, and we'll be talking about it a bit later. We can use hyperspectral sensors for species-level plant and animal detection. I used to work on some of this previously in my previous life when I was working on using hyperspectral data for detecting crop pests in large orchards. We can use LiDAR data to look at 3D forest structure analysis and biomass estimation. This is really important for some of our carbon accounting. We use drone-based monitoring for rapid, high-resolution ecological assessments. This is often when you need extremely quick data. It's a little bit more expensive than using something like a satellite, but they are available and they can often cover really large areas quite quickly. And then we have satellite and radar, which is used for tracking flooding, soil moisture, and wetland dynamics. You might have seen something like this perhaps in the news when there's been a large dam that's burst, and you'll see kind of things online where they show you exactly where the flood is expected to be or how the waters have moved over the last couple of hours. That's often done using satellite radar. We also have global satellite constellations which enable near real-time ecosystem monitoring. So thinking about what's coming next, we also need to think about our current limitations. So it's not just what can we do, but what can't we do? So we know that there are a few things that we struggle with remote sensing, and particularly here in the UK, one of the biggest challenges is cloud cover. So trying to find an image taken at exactly when you want it that also has no cloud cover can be a bit of a challenge. Sometimes you also have vegetation, terrain, or even shadows that may obstruct your features. And even though we are being able to do a lot more with the resolution we have now, and we're getting better and better resolution every day, there are still certain spatial resolutions that aren't quite right for what you're trying to do. So for instance, I couldn't necessarily count the number of grass species from space using a satellite yet, I'll say, but in the future, maybe we will. And then there's also a lack of long-term data sets for ecological change analysis. Now, this isn't a problem that is limited to remote sensing. I'd say this is a problem across the sciences. But because technology changes so fast, a lot of the data sets are collecting different data. And so you don't have really a long-term record where you can go back and you've collected the data in exactly the same way. And then finally, another limitation is cost. Although the cost is coming down, it can still be expensive to acquire satellite data, especially if you want to task it. So that means if you're not willing to look backwards and say, well, use an image collected in the last year or so, but if you wanted a specific date at a specific time, particularly in the future, that can be very expensive. So what are some commercial uses of remote sensing? Well, right now it's used in forest management for timber inventory and valuation. It's also used for deforestation or fire monitoring. We use it for carbon accounting as well in the forestry sector. For environmental consulting, we use it for wetland delineation and monitoring, habitat mapping, environmental impact assessments. Often desktop studies are done using remote sensing. We use it for urban land planning and land use cover mapping, infrastructure and asset management, maybe using remote sensing to map their assets, as well as conservation and wildlife monitoring. So in terms of poaching and illegal activity detection, remote sensing is often used, as well as we can follow migratory patterns and populations as they move across large areas, habitat change quantification, as well as invasive species detection. We also use a lot of remote sensing in resource exploration, in mining, as well as in precision agriculture. So where might remote sensing be going in the future? Well, we know we have some emerging sensors. We have thermal sensors that are coming in. We have new combination LiDAR hyperspectral sensors, which will allow us even more advanced analysis than what we can do now. We have increased access to commercial space platforms and cloud computing, as well as improved sensors. There is a new constellation of hyperspectral satellites that's launching in the near future, and that should change at least what we can get commercially from a hyperspectral perspective. There's also improvements in processing power and algorithm efficiency. So it's not just on the actual satellite side, but also how we process this data. And then finally, what I think is really changing and where things are getting very exciting is how we are integrating remote sensing and AI with more technology. So if we think about the Internet of Things, and even as we get a little bit into like what we're doing here at BNG AI, how we're integrating that technology into the app that you can carry around on your phone and use in your day-to-day work. So, which brings us to a case study I want to talk about where we have integrated technology and ecological expertise, because that's what we believe in here at AI Dash. So we believe that the fusion of advanced technologies like remote sensing and AI, along with deep ecological expertise, will unlock powerful capabilities for environmental monitoring, analysis, and decision making. So with that in mind, we're going to talk through a case study here, the affinity water. So Atkins-Realis commissioned AI Dash to work with Affinity Water combined on a natural capital account for the entire Affinity Water estate. And we did it using remote sensing technology. So the first thing we did was we calculated the BNG score. So we assessed all the habitat within Affinity's land use area. So they had 456 areas of interest in total, and we collected high resolution satellite imagery for the entire estate. The entire area was then mapped per DEFRA BNG guidelines into the DEFRA habitats, and we created a baseline which could be more easily ground surveyed and updated over time. We then use that baseline to calculate their natural capital value using the Environment Agency's NCRAT model and our platforms. And what we ended up with was a natural capital account for the entire estate, which allowed them to baseline where they were. And so at their current baseline, they had a biodiversity and carbon stock at over 444 million, as well as ecosystem service values in the excess of 290 million per year, as well as a natural capital NPV of 9.14 billion over 100 years. And so it was possible to work out the entire value of the estate before we had boots on the ground. And over time, what they will do is they will use our maps and our technology to slowly update this natural capital estate and to move it from an AI baseline into a field validated baseline. So we understand that remote sensing is a tool and not a replacement. So remote sensing and AI approaches cannot replace humans. We believe in automating the boring stuff, and that these tools are as good as some of good at some of the things that we are really bad at, i.e. data collection, data syncing, precisionally drawing polygons, etc. And it's a new way of approaching a problem. So they do require a different type of expertise and a breadth of expertise in order to harness them. Our ecological skills that we've developed as ecologists are not going to not be needed. In fact, they're even more needed. It's just a different way of applying them. And while the tools are not their answer themselves, a bad worker will often blame their tools. Okay. Well, with that in mind, then I'm going to pop into the quick demo and the sort of talking about what BNG AI does. So we at BNG AI obviously believe in AI as your co-pilot for BNG. So how do we harness technology in our product? Well, we have rapid and assessment BNG assessments using satellites and AI. Our quick assessments with interactive planning allow you to know your true BNG potential on site. We have fast and accurate ecologist-led condition assessments with a smart mobile app that allows ecologists to collect data in the field and sync them back to the platform. And then the important part is that our platform incorporates the condition assessment. So it's not just about the map. So once everything is uploaded onto the platform, you are able to take the app to site. You can answer all of the condition assessment questions, capture photographs, and all of it is embedded inside the platform. You don't have to leave to add condition sheets. You don't have to sync that data back, and you don't have to carry any paper and pens with you in the field. We have a simplified CAD overlay function, which allows you to bring in any of your development CAD onto the site, which allows for easy planning and highly interactive visual BNG planning, so you can see the changes on the site as you draw the plan. This is all supported by an automated generation of the BNG metric and automated BNG report wizards. So our accuracy tends to be very precise because it comes from a remote, very positionally accurate data. We use historical imaging for seamless project baselining, even mid-project. So if you had started a project, for instance, or if there was a suspicion of prior degradation, we could go and we could do the baseline for any date that was desired. So if a client has started the development and we need to know what was there before, we'll set our historical imagery 2 years back and we'll map the site as if it was prior to the development starting. We're also compliant with multiple standards. In this case, what's most appropriate is the DEFRA statutory metric. But we can also track biodiversity, carbon, and natural capital metrics like flood mitigation and pollination, as we showed you with the natural capital example. But how do we ensure the quality in our BNG AI preliminary maps? Well, our templates, processes, and calculations are all based on DEFRA guidance. We combine high-resolution aerial imagery with publicly available and bespoke data sets, including things like ordnance survey, priority habitat inventories, etc. We also often have our outputs sense-checked by real ecologists. This allows us continuous improvement for our ecology reviews. And we're always improving as we scan more areas, learning from the survey app as data comes in. We've scanned over 100,000 hectares of biodiversity across 20,000 sites so far. And how do we ensure quality in our reports, especially those that are going to be supporting planning and sent to the LPA? Well, most of our templates and processes, calculations are all based on DEFRA guidance. The BNG survey app also allows the ecologist to validate our preliminary habitat maps on site and complete the condition assessment, bringing the preliminary AI map into a field-validated compliant baseline, which is ready for planning. BNG AI then brings any reports that are submitted in support of planning to you using a wizard, and they will be completed and signed off by the ecologist who has visited the site, the same way a regular report will. So this is what I was talking about with optioneering. So you can enable site or plan selection. You can also avoid the largest impacts, which is very much in line with the mitigation hierarchy. So as we said, we'll often have developers come to us and they'll go, okay, great, we'll look at the site, and then they'll see that there's a fen on it and go, oh, wow, that has an irreplaceable habitat. Perhaps we shouldn't buy this particular site. And I always see that as evidence of the mitigation hierarchy actually working. We're seeing the developers use remote sensing data in order to enable that avoidance part of the hierarchy. We'll also provide bottom-up impact analysis to predict any planned success. And we have a tool set that is designed for everybody, not just the ecologists, but also the field staff, anybody else, architects, anybody who's actually working on BNG. And for me, that's something that's like quite important, because BNG really represents an opportunity to get all the stakeholders in one room. And quite a lot of our processes and ways of working in the past have really focused quite a lot on the ecologist's voice. And the success of BNG means that everybody is able to get into one room and work on this together. Right, so the idea is that we are using AI as a co-pilot for BNG as opposed to actually doing the BNG. So I'm going to go quickly flick through these. This is a little flick through of what our platform actually looks like. So when we create a preliminary baseline for you, what we'll do is you'll drop us an AOI and we will scan the area, and then this is what you get delivered. You get your overview and your baseline. You can view it, you can poke on it, you can click on every habitat, you can change some of the things. So you can check the condition assessment, you can analyze, you can add footnotes, anything that may be interesting to you. And all of that is done if you wanted to run various scenarios. So what some of our clients do is that they will get our preliminary habitat map, and they're not quite ready to send ecologists to the ground, but maybe they have 3 sites that they want to evaluate and they're not quite sure which one they're going to purchase, and they want to make sure that they can achieve 10% BNG on whatever site they do purchase. They will run scenarios across 3 sites. Maybe they'll run multiple scenarios on each site, and therefore be able to make decisions as to A, which site they want to purchase, and then B, exactly how they might go about developing that long before they've even had boots on the ground. We'll also include soil types on our platform. These are obviously integral to the success of any plan you're going to make. It's always good to know whether you have the correct soils. If you wanted to create coastal floodplain grazing masks, for instance, you wouldn't be able to do that if you didn't have the right soils. So we provide information on soils. This is from the National Soil Layer from Cranfield University. We also allow the user to be able to review their habitats. So you can either do this by individual habitats or by groups. It'll also allow you to kind of visualize the biodiversity units for each group of habitats. The app then goes to the field. So you may be familiar with other survey apps that are available. Ours works in a very similar way. The map gets loaded on. You can change any of the features you want. As I said, you can answer all the criteria. You can cap the photographs, and it's all held. You can split habitats, you can merge. And when you're done with all of that, it'll sync back to the platform, and then you can go and you can set any of your final conditions. You can add in the strategic significances on the platform. All of this is editable. You can change the habitat itself, everything. You can see it's all drop down menus. So if I wanted to change this urban to a grassland, I could do that. You can play around with different conditions to see what the change in uplift might be. And then you can plan your uplifts to get your 10% gain. So you can ensure, we'll often have clients that will load the same site 3 or 4 times and then do like a low, a moderate, a high, and a high risk scenario, depending on exactly what they want to do. Finally, plans can be reviewed and approved, and then we will generate the submission ready reports for that site using our documentation as well. All right. That pretty much takes me to the end, so I'm going to stop sharing. Before we wrap up, if you're interested in finding more flexible paid survey work, I'd really recommend checking out the BNG AI Ecologist Partner Program. It's something we launched recently, and it's really simple. We have lots of field ecology projects popping up across the UK, and we match our partners with local opportunities. You can pick the ones that suit you, and you'll also get free access to the BNG AI platform, a range of resources, and support from our in-house ecology team, myself included. It's a great way to stay focused on the fieldwork you enjoy without getting bogged down in admin. If you want to find out more, just scan the QR code on the screen or click the link in the chat and fill out a quick form. Now, apologies, but we're running short on time and we have to wrap up. But if you have any questions, feel free to get in touch with us, hello@ai-.uk, and we'll be happy to help. Thank you, everybody, for attending. It was lovely.